Hello everyone, welcome to this series of lectures. I'm Ragini, and in this series of lectures, for 3 lectures, I'll be talking about the deformation theory of instantons on nearly G2 manifolds. So the plan for these talks, I'll break them down in 3 parts, and in the first lecture, we'll be discussing about the introduction to nearly G2 structures. So I'll start with a very basic introduction to G2 structures, and then we will focus on the main type of G2 structure that we are concerned about, that is nearly G2 structures. So in this lecture, I'll be just talking about just setting up the notation and talking about what are G2 structures and what all things we can do with manifolds with G2 structures. We will look at 2 equivalent definitions of G2 structures, one with the 3 form, the differential geometric sort of definition, and the other one is which comes from a spin theory. So we will look at that, and then in the next lecture we will start discussing about the gauge theory. So this is lecture 1, and in lecture 2 I'll be covering these 2 topics, that is gauge theory on G2 manifolds, and we'll also talk about the infinitesimal deformations of instantons on nearly G2 manifolds. I'll define each and everything. I'll define how what is a G2 instanton, and we will also see how we can describe the space of infinitesimal deformations. And then for the third lecture, we will be looking at a very specific example, and we'll be dealing with the homogeneous connection on homogeneous nearly G2 manifolds, and we'll see how we can explicitly describe the space of instantons on nearly G2 homogeneous manifolds. So this will be the third lecture, and so this is the first lecture. So today it will be very basic. We'll just focus on introduction. All right, so I plan to keep each lecture between 15 to 20 minutes. It's not very hard and fast. I will just go along with the material, but this is what I aim to do. So okay, so let's start. And so as I promised, I'll start with a very brief introduction, and the first definition I have is the definition of a G2 structure, any G2 structure, nothing to do with the nearly term here. Okay, so first of all, if we are talking about G2 structure, we are focused only on dimension 7 because that is the only dimension in which a G2 structure can exist. And so for us, if I say manifold M, it will always be a smooth 7-dimensional manifold. And we define a G2 structure on M is defined using a 3 form, which is non-degenerate. Now we know what is a 3 form, but we need to understand what do we mean by non-degenerate. And by non-degenerate, I mean that if suppose I have a set of local coordinates x1 till x7 on my manifold, then we can define this 2 tensor B by this formula. Here you can see on the right hand side, this is a 2 form, this is a 2 form, and this is a 3 form. So in total they give a 7 form. So it is a scalar multiple, or not a scalar, a multiple of the volume form, which is given by this, and thus this B defines a 2 tensor. And also you can see here, since these are 2 forms, we can very easily just shuffle them, and without changing any sign, that means this 2 tensor B is symmetric in I and J. So using this formula and the 3 form phi, we can define a 2 tensor. Now this we can do for every 2 form, with every 3 form. So this has nothing to do with the non-degeneracy condition. What non-degenerate actually mean is that now this symmetric 2 tensor that we have defined on our manifold M, it actually defines a symmetric bilinear form or a metric on the manifold. So now this B depends on coordinates, it depends on x1 till x7, but this G, now we can define it using this formula, and this is free of coordinates, or basically free of choice of coordinates. So so this is how we can define a symmetric bilinear form. And now we say that our manifold is a G2 structure if this bilinear form G is a Riemannian metric. So we started with a 3-form phi. We defined a symmetric 2 tensor using this 3-form phi, and then if we define a symmetric bilinear form in a coordinate free fashion, like just like this, and if that G is a Riemannian matrix, then we say that phi is non-degenerate. And this is how, so from here you can see, and we say that phi is a G2 structure if phi can define a Riemannian matrix in a similar way. So this, and if phi does this, we say that it's a G2 structure. So in summary, what we have is, if we have a G2 structure, that means that we will have a non-degenerate 3-form phi, and that non-degenerate 3-form phi will not only define a metric G phi as we just did above, but it will also define an orientation. And both of these are done in a highly nonlinear way, as it's very explicit from the expression of B. So from here we can see that the definition of the metric using the 3-form is highly nonlinear, but we can certainly define a metric and an orientation given a G2 structure. And since we have the metric and the orientation, we can use them together to define what is known as the Hodge star, which takes P forms to n minus P forms, and does it. And now, if we apply the Hodge star to the 3-form itself, then we get a 7 minus 3 4 form, which we will denote by psi. So this is what a G2 structure on M is. It's just defined simply by, we just need a 3-form, which itself defines everything. So it defines the metric, it defines an orientation, and thus it also defines a Hodge star, which if we take the Hodge star of the 3-form itself, we get the 4-form psi. So this is the one of the definitions of the G2 structure. We will later see another equivalent definition of the G2 structure using spin structures. Okay, so let's move on. So now, once we have a G2 structure, right, I will always denote a manifold with a G2 structure phi like this. So M is the manifold and phi is 3-form. So that's the G2 structure, and the 4-form we'll always denote it by psi. So once we have a G2 structure, and now the question is that why is known as the G2 structure. So the answer for that is that the stabilizer of this 3-form phi is the exceptional Lie group G2, which is inside S07. So this is the reason that why this structure is known as a G2 structure. So this everything is preserved by the action of the Lie group G2 on the tangent bundle. All right, so since we have this action of the Lie group G2, we have this decomposition of the space of 2 forms into irreducible representations of G2, so of the Lie group G2. So here we have, so the space of 2 forms, it decomposes in 2 subspaces, one of 7 dimension and one of 14 dimension. So these dimensions are pointwise. So at each point we have this decomposition of the space of 2 forms, and the 7-dimensional is just a irreducible 7-dimensional representation of the Lie group G2, but this omega to 14, this is isomorphic to the adjoint representation of the Lie group G2. So the representation of the Lie group G2 on its Lie algebra, that is this omega to 14, because that's the dimension of the group G2. And via the Hodge star, we have this isomorphism between omega 2 and omega 5. So this is what is represented here. So omega 5 will have a similar decomposition. It will also decompose an omega 5 7 and omega 5 14. And then similarly for 3 forms, we have this decomposition, but now the decomposition has 3 pieces. So the first irrap is just the trivial irrap of the Lie group G2, the 1-dimensional. The other one is again just a 7-dimensional representation of the Lie group G2 on R7. And the third one as a subgroup of S07, and last is omega 327, which is again a 27-dimensional irreducible representation of G2, that is given by the traceless symmetric, it's on the traceless symmetric elements on R7. So this is how any 3-form decomposes when we have this action of the Lie group G2 on a manifold with a G2 structure. And again similarly we have the similar decomposition for 4 forms. And now, so the only forms left now are omega 1, omega 6 and omega 7, but omega 1, omega 6 and omega 7 or omega 0, they are all irreducibles. So there is no decomposition there. Okay, so this is how we have this decomposition of the space of forms. The most important form for us will be this omega 214, and we just this is, we'll see later on why is it important, and this is just the joint representation of the Lie group G2. Okay, so now since we have this this decomposition of forms, we can use this to define what are known as the intrinsic torsion forms, or the torsion of the G2 structure, of the G2 structure phi. And how do we define this is we just take the exterior derivative of the 3 form and the exterior derivative of the 4 form. So now this is a 4 form and this is a 5 form. So we know that any 4 form we can decompose it in 3 parts, and these are the three parts of any 4 form. So the first one is in just omega 4 1, the second component tau 1 wedge phi is in omega 4 7, and star of tau 3 is in omega 4 27, and the subscripts, so tau I is an I form. So that's how the subscripts are defined. So basically tau 0 is just a smooth function, tau 1 is a 1 form, and tau 3 is a 3 form, and this tau 3 is in omega 3 27, and tau 0 is just a function, and tau 1, as I already mentioned, is a 4 form. So this is just the decomposition of a 4 form in these 3 components, which we can do for any 4 form. So we can do this for the 4 form d phi. Similarly, for d psi, since it's a 5 form, we can decompose it in 2 components. The first component, again, this is in omega 5 7, and this one is in omega 5 14. So omega 2 here is the tau 2 here is in omega 2 14. So when we take the Hodges star, we land up in omega 5 14, since Hodges star is G2 invariant, and these are irreducibles of G2. So here the one you can observe that this tau 1 and this tau 1 is the same, and that is because phi and psi are related. So psi is just the Hodges star of phi. So they are related, that's why we get the same tau 1 in both of them. So this is a non-trivial computation that one can do, but once we do this, we get these 4 intrinsic torsion forms: tau 0, tau 1, tau 2 and tau 3. And since there are 4 intrinsic torsion forms, we can have 16 classes of G2 structures depending on which is 0 and which is non-zero. So we can just say that tau 0 is 0, like if everything is 0, then we get torsion free because there's no torsion. All the intrinsic torsion forms are just 0. And similarly, if one of them is 0 and all rest are, one of them is non-zero, rest are 0, and so on and so forth. So we can have 16 classes. So 16 classes of G2 structures. So since there are 4 intrinsic torsion form, that gives rise to these. And today our focus will be on today and basically for this lecture series, our focus will be on nearly G2 structure, and that is the case when only tau 0 is non-zero. Otherwise everything is 0. So when tau 0 is the only non-vanishing torsion form, then the equations that we get, you can see very easily from here, is that d phi is just tau naught psi and d psi is 0. So these are the equations that we have for nearly G2 structure. So if the 3 form phi satisfies this equation, then we can say that that phi is nearly G2. One thing that we can also observe from here is that if we differentiate this this d phi equals to tau naught psi, then the equation we get is just that d tau naught wedge psi is equal to 0. But now d tau naught is a 1 form, and the wedging with psi is an isomorphism from omega 1 to omega 5 7, and that's why if d tau naught wedge psi is 0, that implies that d tau naught is 0, and which if I assume that m is connected, then that means that tau naught has to be a constant. Or if m is not connected, we can say that tau naught has to be a constant on each connected component of m. So you can see from before that that we get both of these equations, and since d psi is 0, we get that we can have the equation that d tau naught must be 0 as well, and then tau naught has to be a constant on each connected component. So it can be any non-zero real number, because if it's 0, then we just get the torsion free case, the no torsion, the holonomy G2 case, because if there's no torsion, then we know that the holonomy of the G2 structure is inside the Lie group G2, is a subgroup of the Lie group G2. But if there's torsion, then the holonomy is not inside the subgroup G2, and it's just inside the group SO7. So from here, from now on, we will just assume that tau naught is non-zero. So whenever I am saying nearly G2, I am assuming tau naught to be non-zero. So since we have this tau naught to be non-zero, we can actually scale it to any non-zero real number. And how we can do this is we can change the sign of tau naught by just changing the orientation. And we can also scale tau naught by just rescaling the metric. So by just playing with the metric and the orientation, you can fix or you can choose tau naught to be any non-zero real number. And so for us, we will choose tau naught equals to 4. So this is our assumption. So we will choose that tau naught equals to 4. So the definition for the nearly G2 for us would be that d phi equals to 4 psi. And once we have this, now we no longer need d psi equals to 0, because that's just implied by this d phi equals to 4 psi. Alright, so this is the definition of nearly G2 structure, one of the definitions for nearly G2 structure. And here are some nice facts about nearly G2 structures, which are nearly G2 structure, and of course manifolds which have nearly G2 structure. I will call them nearly G2 manifolds. And there are some very interesting facts about these manifolds which make them worth studying. And the first fact is that nearly G2 manifolds are positive Einstein, which is again itself a very much studied class of manifolds, very useful in physics. And it's positive Einstein, and the Ricci of it is just given by 3/8 tau naught squared G. So here this G is G phi, basically the metric defined by the 3 form phi, and the Ricci is also of the metric G phi. So the Ricci is just a scalar multiple of the metric, and that's why it's positive Einstein, and the scalar is also positive, as you can see here. Another interesting fact which we will see actually is that nearly G2 manifolds admit killing spinors, and in fact 2 implies 1. So whenever we have killing spinor on our manifold, the manifold is Einstein. So the second actually implies 1. And the third very interesting fact which make them important for the study of special holonomy manifolds. So just a reminder, if for nearly G2, so I will abbreviate nearly G2 as NG2. So for nearly G2, the holonomy is inside SO7 and not G2. So these are not holonomy G2 manifolds, only the torsion free is holonomy G2 manifolds. But the cone over a nearly G2 manifold is actually a spin 7 manifold. By that I mean that the cone has holonomy inside a spin 7. So that's why it's although nearly G2 structures are like manifolds with nearly G2 structures, they are not a special holonomy, because the holonomy is inside SO7, but the cone over these manifolds are a special holonomy. So they are very much related to the study of a special holonomy. Okay, so these are some nice facts about nearly G2 manifolds to just justify why one would care about them, but they are interesting on their own, even if we do not care about any of these things. And so since we have talked so much about nearly G2 manifolds, it's good to see some examples, and there are plenty of examples. There are infinite families of examples, but some examples which are very well known or much studied rather are, first of all, the round sphere, S7, and then we also have the squashed sphere, and then there's an homogeneous, so all of these are homogeneous examples which I have mentioned, and then we also have the Bourget space, which is just SO5 mod SO3, and then there is this family of nearly G2 spaces which are known as the Orlov-Volok spaces, NKL, which is just SU3 mod U1 KL. So this U1, it's embedded inside SU3, and the diagonal entries, they depend on the co-prime integers k and l. So these are some examples of nearly G2 manifolds. Okay, so let's move on. So we have seen that if we have a G2 structure on M, then so far we just said that it's a three form, it's defined using a three form phi, but if we have a G2 structure on M, then it is orientable, that we have seen, but it's also spinable. So the condition of existence of a G2 structure is that the first and the second Whitney class must vanish, and since this is the case, then we can talk about the spinor bundle on the our manifold M. And not only we can talk about the spinor bundle, it is we can define a G2 structure using a unit real spinor eta. So since so far we have defined the G2 structure using three form phi, but we can do so equivalently using a unit real spinor eta on SM. So since this is so the spinor bundle on a 7-dimensional manifold is a rank 8 bundle, and if we have a G2 structure, which now we will denote by this spinor eta, we have this decomposition of the spinor bundle in a rank 1 and rank 7. So this is rank 1 and this is rank 7. In the rank 1 and rank 7 spinor bundle sub bundles, and which is defined using the spinor eta. And I say that these definitions are equivalent because you can define the three form phi then using the spinor eta. So okay, so this is a typo, this should be eta, I'm sorry, so it should be x dot y dot z dot eta comma eta. So this is just the inner product on the spinor bundle, so or the Clifford inner product. So this is how we can define the three form phi using the spinor. You can do the same thing, you can define the spinor eta using the three form phi. The expression, I have not written it down here, but that can also be easily done. So you can go back and forth, you can define the G2 structure equivalently using the spinor eta. And since the definitions are equivalent, we can define the torsion of the G2 structure by using this spinorial description as well, and that is given by this equation. So nabla here is just the lift of the Levi-Civita connection on the spinor bundle, and nabla x eta we can say is an sx dot eta, where s is just an endomorphism of the tangent bundle. And since it's an endomorphism of the tangent bundle, it is again isomorphic to omega 2, and again we can have 16 classes of G2 structures. And for the nearly G2, the equation just becomes that S is delta times identity, or basically delta x. So the endomorphism is just a scalar multiple of identity, a non-zero scalar multiple of the identity, and here this dot represents, so basically in this definition as well and everywhere here, the dot just represents the Clifford multiplication. So this is how we can define a nearly G2 structure. So we have now seen that, and this is the definition of a killing spinor. So a killing spinor on a manifold, it satisfies that nabla x eta is some non-zero scalar multiple of x dot eta. So now if the G2 structure is nearly G2, then the spinor associated to the G2 structure is a killing spinor, and we have this 1-to-1 correspondence, and this is again another proof of why nearly G2 manifolds are positive Einstein, because the existence of the killing spinor, it implies that the Ricci must be a scalar multiple of the identity, which depends on delta, which is also known as the killing constant. So here we have this so this is how we can define a G2 structure and everything associated to a nearly G2 structure using this killing spinor. And as I have already mentioned, that from here again you can see that it has weak holonomy G2 since the Levi-Civita connection. So basically the killing spinor eta is not parallel with respect to the Levi-Civita connection. So if delta is 0, then we get holonomy G2 or torsion free. But here you can see that delta is non-zero. In fact, if we want killing spinor, then delta must not be 0, and thus we get that the Levi-Civita the spinor is not parallel with respect to the Levi-Civita connection, and the holonomy is not G2. And also one thing that so if you remember, tau naught was the torsion form for the 3 form phi, and the delta and the tau naught, as we expected, since they are basically are the same thing, are related by this relation. So this is all I wanted to say for the first lecture, and this was just an introduction to G2 structures, just to set up the notation, the background, and these two equivalent definitions, because in what is coming I'll be using these definitions interchangeably, whatever seems much better in the circumstance. Alright, so I'll just stop this lecture right here, and I'll start the next lecture, which will lecture 2, and that would contain basically this is just a basic introduction that will be more towards the deformation theory of instant tones on nearly G2 manifolds. All right, thanks for listening. Bye.